My name is Camilla Dominighetti. I am the Biology Manager for Cell Line Development at Advanced Instruments, and this is my colleague.
I'm Rick Zampa, and I am the Field Application Specialist for the Biotech Osmometer portion of our portfolio. Thank you, Camilla, and welcome everybody. I'm going to go on to the next section of our presentation. Osmolality is a key quality attribute in cell and gene therapy cryopreservation. First, a quick agenda, an overview of osmolality, some cryopreservation basics, and then how osmolality fits into the cryopreservation process. So first, osmolality is defined as the concentration of particles or solutes dissolved in a solution expressed in osmoles per kilogram of solvent. Since it's a measure of mass and not volume, it is not affected by temperature, which is important when looking at your process fluids. Solute concentration in process fluids is an important parameter that's required to achieve consistent results. Osmolality is a measure of concentration and therefore a critical quality attribute and a critical process parameter in bioprocessing. The most common way to check osmolality or measure osmolality is with freezing point technology. So we're going to take a look at what freezing point technology is. So as you may know, when you dissolve that solute into solution, it lowers the freezing temperature of that particular solution. Freezing point technology measures that lower temperature, reports it out as osmolality, which is directly related to the concentration of solute in your solution. Freezing point depression is the most accurate and reliable technology, as it uses this freeze curve here to accurately measure each sample and give you a repeatable result. So regardless of your solution or the drug product, if you add the same amount of solute every time, you'll get the same osmolality. If you're taking a solution with multiple constituents and one is in error, it will give you a different osmolality, which means you need to look back at your preparation stages and see where the error occurred. Okay, cryopreservation basics. So when we look at cryopreservation, it's important to understand that it's not the temperature or the time at the temperature that causes the death of the cell. It's actually the process of traveling through the large temperature ranges that occur in the process. It was discovered in the 1950s that this was osmotic shock that was causing the death of these cells. So what is osmotic shock? It is a physiological dysfunction caused by a sudden change in the concentration of the solute around the cell, which causes a rapid change in the movement of water across the cell membrane, destroying the cell. The osmotic stress can be caused either by slow or fast cooling. In slow cooling, ice is formed in the extracellular environment, which is an increase in the solution osmolality. To compensate, intercellular water passes through the cell membrane to the extracellular solution, thus causing cell dehydration and damaging the cell membranes. In rapid cooling, it's intercellular ice formation that causes the issue. The intercellular ice causes damage and insufficient water outflow in supercooling. Osmolality is key to understanding this process and assures repeatable results and the best cell recovery for your cryopreservation process. So what are some of the risks involved with cryopreservation? There's two main issues for the cells: ice crystals disrupting the cell membranes and or fatal increase in osmolality. To mitigate these effects, you need to have two protective actions: the choice of a cryoprotectant, and then an appropriate cooling and thawing process and testing of osmolality in each of these steps. A protected cooling and thawing process, along with optimized cryoprotectant, is key when having an ideal cryopreservation process, whether that's in your CLD banking or in your final fill and finish process. Osmo can be the indicator of the solution specification in these cases, the optimal conditions, and then an indicator of an issue in the process if it occurs. At the bottom there are just a few of the typical cryopreservatives that are used: glycerol, DMSO, ethylene glycol, and propylene glycol. So now let's talk a little bit about the cryoprotective agents themselves. For the conventional cryopreservation, cell injury is related to the high concentration of CPA used, leading to cell damage due to osmotic stress and interruptions in the normal metabolic pathways at superzero temperatures. There's two types of cryoprotective agents: penetrating and non-penetrating. Non-penetrating CPAs act by increasing the osmolality of the environment, for the extracellular environment, which causes cell dehydration, thus requiring a slow cooling process. This then results in a higher concentration inside the cell, which inhibits intercellular ice formation. Non-penetrating CPAs can also be used in the thawing media to prevent osmotic shock and lysis, and to prevent the return of water to the cells, stopping traumatic expansion. Penetrating CPAs are often small, non-ionic molecules that are highly water-soluble at room temperature. These low molecular weight compounds effectively penetrate the cells and prevent intercellular ice formation. Because of their penetrating nature and their ability to interact with cellular components, including enzymes, penetrating CPAs tend to be more toxic than non-penetrating. During warming, a rapid warming rate is preferred to prevent recrystallization, and the removal of the CPA is required to prevent cytotoxicity. Okay, now we're going to take a look at cryopreservation process. The cryopreservation of cells and the final drug product is an essential step to the whole process within cell and gene therapies. Cryopreservation is meant to preserve the integrity of the drug substances and their critical quality attributes, and therefore maintain a high rate of recovery of cells post-thaw. By testing osmolality of the cryopreservatives and solutions before freezing, you can assure the composition is correct, providing confidence in the upcoming preservation step. So in this slide, we're going to look at cell viability as a function of vehicle solution and cryoprotectant. Cells undergoing cryopreservation pass through a period of hypothermia before, during, and after the freezing process. So the role of the vehicle solution for the CPA influences the outcome of cryopreservation and needs to be considered when setting up a cryopreservation scheme. As you can see on this slide here, we have two vehicles. We're looking at EC urocolins and Unisol UHK here. And it's obvious that the UHK vehicle with the 2 molar of DMSO is the most reliable solution to get the best cell viability. In the study, osmolality was tested to assure the concentration of the DMSO, assure the concentration of the final solution, to assure that they got the best cell viability each time they used the 2 molar UHK solution. In this next slide, this is a study that looks at the human erythrocytes and cryosurvival with minimum cell volume and the use of intercellular trehalose. In this study, survival rates increased approximately linearly with minimum cell volume, and that's what you can see here in this chart right here. As minimum cell volume increased, your cryosurvival increased. What they hypothesize is that the free cell volume may act as a barrier to damaging the cells, damaging levels of cell shrinkage during the freezing process. They then decided to take up to greater than 2 millimole, up to 2 millimole, why is it doing, okay, hitting the wrong button. 200 millimolar of trehalose intercellularly into the cells, and that enhanced survivability up to 15% more. So you can see cryosurvivability and over 250 millimolar of intercellular trehalose, and you get better cryosurvivability. Same when you look over here, and you have your over 200 millimolar. In this particular study, they were measuring the osmolality of the intercellular trehalose, and you can see it's actually even more than 200 millimolar. It was up closer to 250 millimolar, where they had the best cryosurvivability in this particular study. So you can see having the assurance that you're getting the right concentration with osmolality testing will assure you're getting the best survivability of your cells. Okay, next we're going to look at cryopreservatives again, just a little bit more deeply. We get many questions asked about how you can test these cryoprotectants if they're made not to freeze using freezing point technology. So we did an internal study on the Advanced Instruments Osmotec XT osmometer, and we were able to measure all of the osmolalities on these particular cryopreservatives. As you can see, the repeatability and precision were very, very good on the results, and it shows that they can be tested on freezing point depression osmometers. The other thing I want to note here as well is you can see the osmolalities is all very different from over 2100 here. down to 1,100 milliosmoles roughly. And it's important to understand this when you're picking your cryopreservative and your cell of interest to assure that the correct cryopreservative is used for your cell of interest to assure there's no damage from the cryopreservative itself. And osmolality will help you get through that. So, to summarize, cryopreservation is a challenging process that is affected by numerous variables and can affect cell viability and recovery. Cryopreservative agents are complex solutions that are difficult to work with, but have to be in precise concentrations for the best outcomes. Osmolality is the one measurement that can be used to assure cryopreservative and the process are in balance to ensure the best recovery and viability out of your process.
I have a question for you about osmolality.
Yep.
So what would be the ideal osmolality for a perfect cryopreservative solution?
I don't think there's a perfect osmolality. That's the problem. As I showed in the one slide, all the cryopreservatives have very different osmolalities, and it really is going to depend on your cell of interest and what you're trying to look at. For instance, the other two slides that I showed that showed the two different scenarios, one was at 2 molar DMSO, and the other one was 250 millimolar of trehalose. So it really is not going to have, it's a complex process. There's probably going to be some testing you'll have to do with each to see which particular concentration is going to give you the best survival rates.
But do you have like a range that works really well during your assessment of this?
Again, in my assessment of it, it's across the board, depending on the cells they're using. All the studies I've looked at, like I said, it goes from 200 millimolar up to 2 molar of DMSO. So, we're from basically nothing to a very high concentration. So we would have to just basically do some research on it and see which particular cell you're looking at, what would be the optimum solution concentration.
So when the osmolality effect is studied on cell viability, the cell viability is observed after 24 hours of recovery or 48 hours of recovery, or because you showed one slide there about cell viability, but it was from paper or it was?
It was from a paper that I took that particular slide from, and I don't remember exactly what the timing was on that particular one, so I could dig back into that and find out though.
Yeah, because after 48 hours, the viability drops, right? Whatever cell you recover. 24 hours, the viability can be 90%, but 48 hours drops and 72 hours can drop further.
Yeah.
So I don't know how accurate you can measure.
Well, yeah, well, like I said, I don't remember the timing on that particular study. I was just using that quickly for representation of that. So you're welcome.
I know from my background that we always dealt with that because of clonogenicity versus cell death, and apoptosis could happen 4 hours, 6 hours, 8 hours. And ultimately, if the cell dies, the cell's dead. So that's the power of a clonogenicity assay, but the problem is most people don't want to do those because they're labor intensive and take a long time.